We're now going to discuss a reasonably complicated topic called thread local storage. So essentially, the idea is as follows. Let's suppose that you are just summing a bunch of integers. So you have a variable called sum with a value of 0, and then you do a parallel dot for. Let's suppose we want to count the sum from 1 to 1,000. So we put 1 and 1,001 here, and then we specify the lambda. So in the lambda, for example, what we can do is we can increase the sum. Now, sum is a shared variable. It's shared between every single thread that will want to increase it. So if you do want to increase it, you have to do something like interlock.add, do ref sum, and increase it by the value of x. So this is how you would do it. Unfortunately, the problem here is that there is a lot of access to the sum variable. So every single task is doing the access at every single point. Now, why can't we calculate a partial sum on each of the tasks and then just add the partial sums using interlock? That will certainly decrease the amount of interlocked calls necessary. And in fact, what happens is the .NET Framework gives you such a functionality. And it does look a bit complicated, I have to add. So that's what we're going to see right now. So we'll do a sum once again. Sum equals 0. And there'll still be some interlocked code, but for the most part, what the parallel loop is going to look like is completely different. So first of all, and we're going to take this slowly, the parallel loop is going from 1 to 1,001. So we have 1,000 elements. However, the next argument is going to be something completely different to what we've seen before. You can see that the parallel for has lots and lots of overloads. There is a huge number of overloads here, and if you fire up code completion, you'll see that there are plenty of different options here. So the option that we're actually after is the first one, and you might be surprised that there is no arguments in a lambda here, and that's because this lambda is an initialization lambda for thread local storage. So the idea is that for each of the separate threads, you can have some sort of storage which is local only to that thread and not accessible to other threads. So the idea is that instead of doing interlocked on the sum 1,000 times, which is inefficient, what we can do instead is we can take each of the threads and calculate the partial sum. So the sum of the range from 1 to 1,001 that's been allocated to that thread, we calculate the sum in an ordinary fashion without any interlock calls. And when we got this partial sum, that's when we do the interlock. So the initialization of this sum is done using this particular lambda function, and we initialize the local storage value with a 0. So that's the value that each of the threads is actually going to increase. Now, the next part is, of course, how you update whenever each of the threads executes. So the lambda for the update part is fairly complicated. Instead of taking just one argument, which is the counter, we now take a whole 3 arguments. So the first argument is, in fact, the counter. That's the value of x. Now, the second argument happens to be the state variable. That is the variable that is actually being used to show the state of the parallel execution. We cannot avoid having this variable even if we don't care about using it. And the final argument, and that's